Mechanically, calculating flux is actually kind of similar to calculating surface area. It's just or calculating mass of a surface. If we have a vector field, f of x, y, z, and we have a surface with a particular parameterization, phi of uv, then what we do is we calculate. First, we plug in our parameterization to our vector field. This calculates the kind of vector field at our position. And what we do then is we also calculate the normal, this cross product, TU cross with TV, and then we take the dot product of those. And then we integrate that whole thing up. So when we do this calculation, the vector TU cross with TV, the cross product of these two tangent vectors, is a normal vector for the surface. This is what's going to tell us which direction is up and which direction is down. If the total integral is positive, then that's going to tell us that the flux is, or the rate of flow is mostly outward in the same direction as the normal vector. And if it's negative, the net rate of flow is in the opposite direction. So the reason this formula works is the following. We do it by approximations because we're doing it with an integral. So the thing we need to know is, how do we calculate the total rate of flow of a fluid through a little parallelogram? Well, the total rate of flow is proportional to the surface area times the speed of the flow that's in the perpendicular direction. And to get the speed of the perpendicular flow, we need to take the flow and break it down into a parallel component and a perpendicular component. Here, if this is the normal vector, TU cross with TV, like that, then what we want is to multiply our surface area of the parallelogram by the speed of the flow, the length of this blue vector, times the cosine of this angle between the fluid and the normal. But the surface area is the length of TU cross with TV. The speed of the flow is the length of this vector f of phi of uv. And the cosine of the angle between them, cos theta, is just cos theta. This product of these three things is precisely the dot product of our vector field. That's why the formula works, is that all these contributions come together in this magical way and give us a much simpler formula than we might initially expect.